Red light. Okay. We were talking. Anybody have any questions first? Yeah. About circuit tests? Non-destructive tests. Yeah, that's actually in the. Actually, there's not as much as there should be. However, I am going a little bit faster now that I'm making some overheads this year. So maybe I'll be able to include some. Still plan to finish by Halloween. But you still haven't heard the last 3 tapes on 3371, and that covers some of that covers non-destructive testing, but not in as much detail as the previous year. So if we don't do that, and I don't have time between now and Halloween to do it, then if you actually go on the website for last year, 2001, and go to 3371 and go through the last 3 lectures there, I go through more non-destructive testing on that. So we'll cover that. We were talking about soldering, just to finish up. You got to control the solder composition fairly tightly. And you say, well, where do these impurities come from? Well, when you essentially run the printed circuit board over the solder bath, there's a little bit of dissolution of the solder of the other components on the printed circuit board. You may have gold-plated components on the printed circuit board. You certainly got copper on the printed circuit board. You've got nickel-plated components. You've got all kinds of things on that printed circuit board. In fact, I sometimes describe a printed circuit board as the ultimate composite material. It's very, very difficult to recycle in the sense that you start out with a glass fiber and plastic laminate. That's the board. You then put other types of polymers on top of that, polyimides and things that have good high temperature capability. You then put some copper on that, and some of those copper wires go down through the board in many cases. And then you get to the board itself, and what do you have? You have ceramic chip carriers. You have all kinds of different metal components and ceramic components. What's a capacitor? A capacitor is either a piece of aluminum that's been anodized to form a thin oxide skin and then rolled up in some sort of jelly roll, or it's a piece of tantalum they do a similar type of thing to oxidize its surface and make it a capacitor. If you look at and then you got silicon and all the semiconductors, you got metal, ceramics, polymers, and electronic materials. You've got all your materials classes on a printed circuit board. And as a result, and they're all mixed in intimately, in very complex geometry, it's virtually impossible to recycle a printed circuit board in any economical way unless in the old days, we used to put enough gold on them that you could melt the whole thing down, and even if it was only 0.5% gold by weight or even 0.1% gold by weight, that's better than what you dig out of the ground, and you could just melt the whole thing. And in fact, there's a refinery down here in Attleboro, Massachusetts, gold refinery, and you go in there. I haven't been there for 10 years now, but you used to go in there and you see all kinds of old computers that were being recycled for their gold content. Unfortunately, for recyclability, they've gotten the gold out of a lot of these things, and so now it's not even worth recycling them. So that's somewhat of a problem. But anyway, you'll pick up all types of impurities over time, and so in these wave soldering machines, you have to every now and then just completely take the couple of tons of solder out of there and send it back to the refinery and put new solder in. Solderability testing is very empirical. I kind of made fun of it yesterday, but it's not very sophisticated. For solder drops below 1/8 of an inch in size, surface tension forces predominate. Well, it's not just solder drops, it's metals in general. And you might think, well, that's kind of a silly rule of thumb, but I would say that, of course, I'm a metallurgist, but twice a year I come across some phenomena that someone's talking about that they don't understand exactly what's going on. For example, I was at a NASA workshop this summer, and they're talking about how they want to build the space station and actually build it in space by doing electron beam melting. And they were proposing, people were proposing to do a study of the gravitational effects on the liquid metal. And I can't remember if they're, well, I don't remember if that was exactly the question, but it basically got down to knowing at what size liquid would surface tension or gravity predominate. And if you're up there and your melted region is significantly less than an eighth of an inch in size, it doesn't matter whether you have gravity or not. Surface tension is going to control things. If it's much greater than an eighth of an inch, if it's a quarter of an inch in size, the thing's going to slump under gravity and things will be different up in space. So it's actually kind of a little rule of thumb that I like to say I run across on a much more frequent basis than I would suspect otherwise. Anybody have any questions on soldering or those types of things? I guess one thing I haven't said about soldering is what type of strength you should expect. Since soldering is a low temperature process, you are always in the creep regime. In fact, Stuart Brown, when he's a faculty member here and used to teach mechanical behavior and creep, used to start off his lecture by coming in with a piece of lead tin solder wire and a little ring stand, and he would hang a weight from the lead tin solder. He would measure the length of the wire at the beginning of class, it might be 12 inches long, and by the end of class it was 13 inches long. Okay, so just in the time of class the thing would creep 10 or 15%. Well, that's a serious problem with all solders, because all solders are operating above 6/10 of their absolute melting point at room temperature. And that means that my rule of thumb that I use is that if the solder is within 100 degrees centigrade of its melting temperature, so if T melting minus 100 degrees C equals room temperature for solder, the stress, applied stress, not yield stress, but applied stress, should be less than 1,000 psi. Now that's not so bad because that's stronger than an adhesive bond in general, but certainly if you start figuring room temperature at absolute zero and stuff, this basically says is if you're at 7/10 or 0.75 or something like that, 75% of the absolute melting temperature at room temperature, then you can't support more than about 1,000 psi. And now ordinarily in other metals that are not in the creep regime, we would think of 10, 20,000 psi. And in fact, we'll get to brazing today. We'll talk about the fact that you can expect 5 or 10,000 psi as a braze alloy strength at room temperature. But solders, you really can't tolerate more than 1,000 psi.
Can you get the thin film strengthening in solders too?
Not really, because of the creep problem. Yeah, it's viscous flow, if you will. You could probably apply the Stefan equation, because it's creep flow, to solders just like you do to adhesive joints. The problem is the solders just don't have a very high viscosity when you get to even at room temperature. They will flow. I mean, if you think about it, you take a piece of lead and you can scratch it with your ballpoint pen, and that means that the shear stress is relatively low. It just doesn't have as many orders of magnitude as some of the adhesive joints, so far as that goes. And I guess I've seen a number of failures where people try to use solder in a structural capacity, and certainly we do on a printed circuit board, but the loads are low on a printed circuit board. Who's pulling on one of those components with 1,000 psi? However, when people are making soldered packages, I mean, you've got a transformer and I've seen people solder it up, and then they pot it up with plastic inside and they heat it up, and the thing operates at an elevated temperature because of the electrical power going into it and the dissipation in the transformer. Some of these things will pop, and it's because all they did was overlap a solder joint. What they need to do is interlock a solder joint. You basically bend the metal, the copper or the steel sheet like this, and that's supporting the strength. And you get the sealing power from the solder. So you get your hermeticity, you keep the moisture out and the air out with the solder, but you get your mechanical strength by screws or lock joints or things like that. So there's plenty of ways to design it, but in general, it's best not to design a solder joint to be the structural component. Now, if we go to brazing, brazing is the same as soldering except higher temperatures, and that means a number of things. First, it means greater flexibility in the choice of fluxes. I think I mentioned yesterday that certain types of metals can't be soldered. Tantalum, zirconium, titanium, things that have very, very refractory oxides are very stable, and at the temperatures of soldering, we just don't have enough thermal energy. We don't have anything that can break down those very stable oxides on the surface. And so we can't clean off the surface. The closest we come is this kind of special case of reaction fluxes in aluminum where you float it off and you get this special reaction between tin chloride and aluminum, and you get aluminum chloride formed. But that doesn't work in titanium. It doesn't work in zirconium and a lot of these refractory metals. However, when you go above 425 degrees centigrade, and in fact most of your brazing is done above 600 degrees centigrade, and some of it's done at 2,000 degrees centigrade. You can braze graphite at 2,000 degrees centigrade. I had a student who used platinum to braze graphite once. Platinum melts at 1,700 degrees centigrade. That was the brazing alloy. That's above the melting temperature of steel. And so I suspect, I don't know for sure, but I suspect some parts of a cruise missile motor, which are all, a lot of it's graphite, has some high temperature brazes in it. Now a cruise missile is a little bit of a special case because it only has to last for about 2 hours, okay? You don't have a long lifetime. So it can operate at very, very high temperatures. And they actually make it out of graphite composites. But anyway, you have much greater flexibility in the choice of fluxes. In fact, virtually any metal or ceramic can be brazed. I don't know of any metal that can't be brazed. And if you look in the brazing handbook, you can braze aluminum oxide, you can braze, in this case, you're not trying to get rid of the oxide. What you do is you have a reactive metal. And one of the popular ones right now is a silver, copper, titanium, where the titanium is 2 to 5%. Braze alloy. Silver copper forms a eutectic at 723 centigrade. You put 2 to 5% titanium in there. The silver copper is a nice silver solder, which is a silver braze, and the titanium makes it reactive. The titanium will eat away enough of the aluminum oxide to allow it to spread across the surface. Not because you're getting metal-metal bonding, but because you're actually forming an aluminum titanate ceramic at the interface. It turns out you can braze aluminum oxide with copper because it forms a copper aluminate on the surface. And it turns out in some of these brazing of ceramics, you actually need a little bit of oxygen in your atmosphere. Not too much, or you'll just oxidize the metal and it won't flow, but a little bit of oxygen will help form some of these oxides that help the wetting at the interface. So virtually any metal can be brazed in many of our ceramics. There are some ceramics that cannot be brazed. I was advising some people in a patent dispute over eyeglass frames. And basically, the patent was written in some way, said, well, that they had to, it was a new way to join something that couldn't be joined by welding, supposedly. Well, then you get into the question, always in patents, what do you mean by the word is, okay, as President Clinton says, what do you mean by the word welding? And maybe I'll come in and talk about that sometime, but the American Welding Society has a definition that welding includes brazing, soldering, adhesive bonding, virtually anything except fastening almost. And so these people basically had a fastening technique and in their patent, and we were looking at patents back from the 1830s where people were making eyeglass frames. And it turns out there's certain types of things that can't be brazed or soldered that are ceramics, and they tend to be things like abalone shell or tortoise shell, or what are some of the other things? There was, some of the thermosetting plastics can't be brazed because these things decompose at the brazing temperature. So something that decomposes, obviously, if the base material decomposes, you can't braze it. But virtually any material that doesn't decompose, you can find a flux and a solder material or a brazing material that will flow across the surface. You can braze with glass. We have glass to metal seals where you actually oxidize the surface of the metal and you want to join that seal to a ceramic so that you can make an electrical feed through typically, and you actually use a braze alloy that is nothing more than another glass that melts at a low temperature. You melt it in there and it wets the two surfaces. That's essentially a braze joint. More base, well, this is kind of the same thing. More base material, because you have a better choice of fluxes, you can have more base metals that can be joined. It turns out, we've already talked about this, the room temperature strength is greater than soldering because it's not in the creep regime. If you take 273 plus 425, then clearly you're above, at the brazing temperature, above at room temperature, you're going to be below half the absolute melting point at room temperature, and therefore you're not in the creep regime. And you can get braze joint strengths, kind of, again, a rule of thumb, just like I consider solder joints never to have a strength of more than about 1,000 psi in service. Braze joints, I usually figure, can take about 5,000 psi. And in certain cases where we get thin joints and contact strengthening, braze joints can take 40,000 psi. And so it's getting up to be as strong as a weld in some cases. Although don't count on that too much, that 40,000 psi. It can be achieved, but only in certain cases. Typically, 5 to 10 ksi is typical strength of a braze joint. It is true metal-metal bonding, so you're getting the primary bonding. That's if we're talking metals as base materials. If you're talking ceramics, ceramics will fracture because they're brittle, and you're not going to get 5 ksi. Now, volatilization of alloying elements. It turns out that we use lots of different materials for brazing, and some of them run into problems because they have different types of materials in them that they can be volatile. One of the most serious ones is cadmium, and there were, until a few years ago, a whole series of silver, copper, cadmium brazing alloys. Again, these are based on the silver copper eutectic, but you add cadmium and you can get that 723 centigrade temperature down to, let's say, 640 degrees centigrade. And dropping the temperature by 100 degrees centigrade means that you can braze things much faster. It turns out cadmium makes this alloy flow extremely well. So it'll fill big gaps and small gaps. It's just a very, very easy braze alloy to work with. The problem is cadmium is toxic, just like mercury or gallium or some of the other heavy metals. And so the tolerances for cadmium in the environment have gone down significantly over the years. It turns out there is still some cadmium around us all the time. There's cadmium in this light switch. Anybody know why there's cadmium in the light switch? There's cadmium in the light switch to prevent fires. It turns out that's typically a 15 or 20 amp switch, right? If you do any home wiring or something that you're probably not supposed to do, but I do it. So anyway, typically a 15 or 20 amp switch, if you making an electrical contact is not really a problem. You don't have any energy to break, and you put the two contacts together and everything's fine. The problem is when you pull the contacts apart, you are interrupting potentially power, right? I mean, the lights were on, and there's a certain inductance in the system. So what does inductance do electrically? It kind of, inductance is the inertia of the electrical system. It doesn't want to change the current. If the current is 0, it doesn't want to increase the current too rapidly. If the current is flowing and it's 10 amps or 15 amps and you break the circuit, it wants to keep flowing 10 or 15 amps, and it decays in a nice little exponential decay. Okay, so the problem is you now break that circuit, you can get an arc that strikes across there. And so if you're dealing with, you can get an arc, and we're going to talk about arcs later, but you need about 10 volts. Well, we got 120 volts, so it's plenty of voltage to generate an arc. And now if the whole circuit's at 1 amp, well, 1 amp arc lasting for even a fraction of a second, is not enough power to really do much damage. But a 10 amp arc that might last for 10 seconds is going to generate enough power to start melting metal. You start melting metal, if there's any combustibles around, you start fires. By the way, where does the inductance come from physically? What creates the inductance? It's somehow related to magnetism, right? If you have a conductor, so if this is a wire conducting electricity, there's a magnetic field around it. If you have no current flowing through it, there's no magnetic field, but if I have current flowing through it, there's a magnetic field, and if I break the current, what happens is the magnetic field has stored energy. The magnetic field is stored energy. It's b squared over 8 pi, 4 pi, 8 pi, whatever it is, per unit volume. And that collapsing magnetic field drives the current to try to keep the current constant, because it wants to maintain the magnetic field, but in fact the magnetic field decays. That's the inductance. So when you shut off the light, there are magnetic fields running around up here along with the current, and as that magnetic field collapses, then it keeps on driving a little bit of current even after you shut the arc off. And that current may last for a few tens of milliseconds, but that can be long enough if I've got 10 or 15 amps to melt the contacts. So what I do at low currents, 10 to 15 amps, or actually at up to 10 amps, I'll just have silver contacts. So why silver contacts and not copper contacts? Well, copper contacts oxidize, and that gives me high resistance. And I can start a fire while the current's going through it, because now I got a toaster oven, right? And basically, just the contact becomes the heating element, and I can melt my contacts together. And then when I try to turn the whatever it is off, it's not very good because I just welded the two together. If I have silver, silver doesn't tarnish or doesn't oxidize in air, and as long as it's not too bad a industrial environment, I don't get a heavy tarnish on there. So silver makes good electrical contacts, pure silver up to about 10 amps. If I want 15 or 20 amps, I have to add about 1% or a 0.5% cadmium to the silver. And it's still not completely known exactly what the cadmium does. People have tried to replace the cadmium with tin. There's all kinds of theories that when you break this arc, some of the cadmium vaporizes and helps quench the arc between the contacts. But you might be able, with silver cadmium contacts, to get up to 30 amps without starting fires. A number of years ago, 15 or 20 years ago, in Sweden, they're very environmentally conscious, and so they found out that they had cadmium in the electrical contacts, and they outlawed cadmium. And they did that for about 4 or 5 years until they found out that the number of homes they were burning down increased significantly. And so they decided maybe a little bit of cadmium wasn't so bad. So if I go flip the light switch on and off, you might increase the amount of cadmium vapor in this room by 1 part per 100 trillion or something, you know. Who cares? You know, if one atom out of 10 to the 12th or something is going to kill you, you might as well just go down and lie down in your casket and in the grave and wait for someone to throw the dirt over you. It's a question of dose, which most people forget about when they worry about environmental things. So anyway, cadmium is a problem. It's a particular problem, it turns out, in brazing, because there's 10 to 15% cadmium, and if someone's actually standing over this thing and breathing this, they actually can get toxic, and they're doing it every day as in a workplace. They can get a toxic level that doesn't usually kill them. Usually gets them so sick they end up on disability or something. But it can be very, very harmful. For a long time, for about 10 years in the 1980s, lots of people were working to come up with replacements for cadmium and silver solders. And for a long time, they hardly sold any. But then it turns out it is such an advantage in productivity that many people have installed the environmental controls, and they're going back to using some of the cadmium silver solders just because of the productivity advantage. It may be that as we try to get lead and cadmium and other things out of the environment, they'll go back and they'll just pay the price of lower productivity because you have to go to higher temperatures. Zinc is another common thing. You add zinc, you can add it to silver solders to lower the melting point, not as low as cadmium. It doesn't give you as flow that's quite as good because it oxidizes too easily. But certainly in copper brazes, essentially brasses are nothing more than brazing alloys to a brazier. And zinc is the primary component in the brasses. Well, the problem with zinc is it will give you what's called metal fume fever if you breathe too much of it. And it doesn't matter whether you're soldering, or whether you're brazing or you're welding on brass. If you don't have good ventilation, you actually see a white smoke, which is white zinc oxide. You know zinc oxide's white if you've ever been to the beach, and you see the lifeguards are all got this white nose, right? And that's basically just a zinc oxide ointment they put on their nose to keep from getting a bad sunburn on their nose. So zinc oxide is very bad if you breathe it. It's not necessarily so bad if you eat it. After all, oysters are about 1% zinc. So if you like oysters, you can get a lot. In fact, you go to the health food store. They sell zinc supplements. So you can down a few zinc pills, and it's one of the minerals that's necessary for health. But if you breathe it as zinc oxide, it will give you metal fume fever. I've never had metal fume fever, but basically you get chills and a high fever, and you start shaking, and it'll last for 24 to 48 hours. I remember one technician I worked with once had it. He says, first you get so sick you're afraid you're going to die, and then you get so sick you're afraid you're not going to die. That it's a terrible feeling, supposedly. However, zinc metal fume fever, so far as I've been able to read, has no long-term effects. Because your body uses zinc naturally, your body will get rid of it. It just doesn't like it coming in through the lungs. It likes it coming in through the stomach. Okay? So your body can metabolize it. The problem with cadmium or mercury, your body doesn't metabolize those. They're not needed in any significant quantity for human health, and therefore they just go to your liver and destroy your liver and other things. Or lead ends up going to a child's brain and messing up the neurons. Another problem with volatilization is not necessarily the health effects, but the fact that if you're doing your brazing in a furnace, the vapor coming off can react with the furnace elements. And I've been through plants where they say, well, we've been brazing this stuff for a few months and our furnace elements have just fallen apart. I said, what's your brazing out? Well, we're brazing with brass. I said, well, why don't you go to a low volatile brazing alloy, a copper tin alloy. Tin has a very low vapor pressure, and you can get the same type of brazing temperatures without the zinc. With the zinc in there, the zinc basically was just zinc vapor in the furnace, and it was alloying with their electrical heating elements and destroying them. So volatilization of the alloying elements can be a problem. They actually even sell silver solders that are silver braze alloys, I should call them braze alloys, that have very low volatiles. The American Welding Society designates braze alloys or brazing wires with a B designation. Welding electrodes are with an E designation, but B for brazing, and silver alloys are BAG. And obviously we call them bag alloys, so you have bag 1, bag 2, you can have bag 12, and that's a specific alloy of silver, copper, zinc, whatever. But if it has a V after it, it means that it's specially formulated from very pure silver or very pure copper, and it does not have any significant amount of easily volatilized elements like zinc, even in minor quantities. And so it's suitable for brazing in a vacuum furnace, because in a vacuum furnace, the volatile elements come off more easily than at 1 atmosphere. Another problem with brazing is because of the higher temperatures, you have a greater tendency for intermetallic compounds to form, and therefore the brittle braze zones. And I mentioned a week ago or so, talked about the cross-field amplifier and how the Navy had been specifying use of a 82% gold, 18% nickel braze alloy. The company found if they went to a 37% gold and 60% copper alloy, something like that, with lower nickel, they got a very ductile alloy, and it turns out to be a transit liquid phase diffusion bond. But what they really did is they got rid of the nickel-3 molybdenum intermetallic when they were brazing the molybdenum to the copper, because they didn't have as high a nickel content in the Braze alloy. You're at higher temperatures, you've got more complex compositions, and you have more intermetallics that form. It's not to say intermetallics don't form in some cases on soldering, but there's no serious ones with lead, tin, and copper. There are when we get to some other things, which we talked about yesterday. Thermal stresses. Because I'm brazing at higher temperatures, I'm going to have greater thermal stresses in the whole alloy. It turns out that a simple way to look at thermal stresses is just say, well, what is, if the strain, epsilon, is going to be proportional to alpha delta T. Well, actually, it's delta alpha between the two materials that I'm brazing. Well, delta alpha for, or alpha for most metals is something like 20 times 10 to the minus 6 centigrade. And for a ceramic, it may have a value of 1/2 of that, 10 times 10 to the minus 6. That means delta alpha is 10 times 10 to the minus 6, or 10 to the minus 5 per degree centigrade. If I multiply that by 200 degrees centigrade as a difference in temperature, I'm going to get 2 times 10 to the minus 3 as a strain. Well, that strain is essentially 0.002. Anybody know what a strain of 0.002 to most mechanical engineers means? 0.002 offset is a, yeah, that's basically the yield strength of the material. That strain is typically close to the yield strength of the material. I mean, that's, I've cheated a little bit on you. It's not that I don't cheat in this course. If you look at a stress strain curve, when it yields right here, sigma y, if you take the offset strain of 0.002, they often will define that offset strain as the actual yield point, okay? So it's, sigma y is up there, okay? It's up a little bit higher. So that actual strain might be 0.004 or something, but another way to look at it is, let's just take, if you take stress times Young's modulus times the strain, and I take, if I'm steel, I've got 30 times 10 to the 6 psi as the Young's modulus times 0.002, and that should work out to 60 ksi as a stress, okay? Just putting in the modulus of the material, I'm going to end up with 60 ksi. Well, 60 ksi is, in fact, a fracture strain for a low-strength steel. It's a reasonable stress for a high-strength steel in a building or a bridge or something like that. So if I did that right, I don't know, you can check my numbers, but you're going to end up with very, very significant stresses with only a couple of degrees, 100 degrees centigrade as a difference in temperature. Well, if I take two materials and take them up and braze them at 700 degrees centigrade and then drop them down to room temperature, they expand and contract at different rates, and that means the braze joint for dissimilar materials is going to have very, very high residual stresses. And as a result, I said up here, yes, you can braze even ceramics, but it turns out the ceramics will often crack on you. And the reason they crack is because of these thermal stresses, which are equal to the yield strength of the material. As a result, if you go, I said that you could get a 5,000 or 10,000 pounds per square inch strength for a metal-metal braze. If you go to ceramic metal brazing, you may not get more than a couple of thousand psi because you've already got the residual stresses between the metal and the ceramic that are going to cause residual stresses that add to your surface stresses and create problems. Now, the last thing that higher temperatures of brazing compared to soldering mean is that you'll get erosion of the base material. And by that I'm talking about the fact that if I've got a joint and I want to get a nice fillet of brazed material in here, then if I go to higher temperatures, it's likely that this braze alloy will diffuse in, and if it diffuses enough, I can end up with essentially almost no base material in between here. And essentially the whole thing could fall apart on me. If this is thin enough and the erosion or co-melting of the braze alloy with the base material as it melts and erodes that at higher temperatures is severe enough, I could have the whole thing fall apart unless it's fixtured properly in the brazing furnace. And in fact, that's why for many years, actually until about 1982, people used, and this next component I'm going to talk about, the 18% nickel, 82% gold alloy as the braze alloy in these shroud honeycomb assemblies. I passed this around before. This is part of a shroud of a jet engine. So the turbine blades are cutting past here, and I passed it around before. You have this honeycomb, and this is about 5 or 10 thousandths nickel-based superalloy honeycomb, which is brazed to the shroud. And as the turbine blades age and grow because they creep over time and get longer, they got high stress from the centrifugal force of spinning around at thousands and thousands of RPM. They cut into the surface, and that creates the seal that keeps the gas from leaking past. So if you want to pass that around again, you can. That until about 1982, they basically used 18 gold, 8 nickel, or 18 nickel, 82 gold as the braze alloy, which, if I remember, that brazes at around 1,000 degrees centigrade, which is about the right temperature range. Well, actually, 800 or 900 degrees centigrade is the operating temperature range. It doesn't oxidize. Gold doesn't oxidize. Nickel's fairly oxidation resistant, but it doesn't erode. It doesn't alloy significantly with the base material, and there's almost no erosion. And so you don't end up eroding this only 5 thousandths thick foil here. So typically that might only be 5 thousandths of an inch thick. If you went in with our typical nickel boron brazes, you'd essentially just melt the whole thing. The boron would alloy with the nickel in the foil, and you basically just end up with a puddle of a mess. Okay, you just melt all your metal together. So what happened was until 1982, they used to use the 82% gold alloy. Anybody know what happened to gold in 1982? Some of you were not very old. Some of you weren't even in school yet, right? In 1982, the price of gold shot up to about $800 an ounce. It had been running around $200–300 an ounce, then it got up to $400 an ounce, and then it shot up to about $800 an ounce. And now you're talking about a very, very, the price of these components was getting very high. So what they did is first they replaced the gold with palladium, which at the time, palladium was fairly cheap. It was about $40 an ounce. That was a lot better than the price of gold. Palladium's not so cheap anymore because they use it in catalytic converters in cars, and actually palladium is more expensive than gold now. So that's just how things change with time as they find applications for different things. So they ended up by 1985, they had developed new alloys, which are based on nickel and silicon and other things. And so that is probably not brazed with gold. In fact, I doubt that the people would have even given me a part that big with gold because it might have had $10 worth of gold in it. It doesn't take very much gold to be worth something. However, back in the late 70s, one of my first consulting jobs for a New England aircraft engine manufacturer, who will remain nameless, was to go in and figure out how much braze alloy was being used when they soldered these types of things together. And what had happened is they were building a military engine that had these honeycomb structures. And those honeycomb structures, I don't know if they'd been around more than 10 years at that point in the turbine engines as they were making them more efficient. But in any case, the technique was to, they'd have the shroud, and they would take this honeycomb foil that they would kind of lay in there, and then a technician would basically take a salt shaker full of this gold nickel braze alloy, and they would shake it in there, just like you're, putting salt on a steak or on a salad or something. So you'd shake this in there, and then they would take some clear paint, from a spray can, like you go to the hardware store and you get Krylon crystal clear. They would spray it in there, and that would hold the powder in place. And then they would do this all 360 degrees around, and then they would put it in the furnace, and the paint would as it burned off, it turns out it was just the right kind of polymer that it would get stickier and stickier, and then it would carbonize, and it would basically hold the braze alloy in place until it actually melted, and you would end up making this nice little joint like this with 82 gold, 8 nickel. Well, the problem the company had run into is there was a big increase in orders, and at the time, all you had to do to get a 50-ounce bottle of this braze alloy was to go to the storehouse, the stores in the plant, and give them a requisition, and they would give you a 50-ounce bottle of gold nickel braze powder. And you start thinking about that. It's 82% gold, so that means it's 41 ounces of gold in this 50-ounce container, which is not much bigger than a Coke can, right? And 41 times $400 an ounce is $16,000. So it was a fairly valuable little Coke can full of, it wasn't a Coke can, it was a little nice little plastic container. But, and it turns out that amount of braze alloy would typically last this technician about once a week. And so his boss was used to his signing a requisition, for one bottle of braze alloy a week. But then production got a little busier, and so he started asking for 2 bottles a week because he was doing a lot more. And then production tailed off, and he thought, what the heck, I'll keep getting 2 bottles a week. One for the company and one for me. And he did this for a year and a half before someone turned him in. And the problem was the company had no idea of exactly how much he had actually stolen, because there was no controls whatsoever on how much he was sprinkling on there. Now, when I went to visit, there was a woman there who, they fired the other guy, actually, they carried him off in handcuffs, but anyway. There was a woman who was doing this sprinkling, and she had to weigh the bottle before she sprinkled, or when she loaded it into the salt shaker. She then weighed the salt shaker. She had a logbook of exactly how much she shook into this each one of these components. And so they now had a big record of every gram that went into each component. So they were now tracking it. But in the meantime, my job was to try to figure out how much he had not used in a year and a half's production, so they could figure out, since this whole thing was bonded and some insurance company was going to have to pay the money back to the government anyway. Turns out the only lawsuits were criminal lawsuits. The guy got 1 year in jail. The person that was carrying it to New York City for him got 6 months suspended sentence, and the fence in New York City, who was receiving it, who probably made all the money to begin with, got nothing, got off completely free. But I think we figured it was somewhere between $1.5 and $2 million worth of gold that he had borrowed on the no return plan. In any case, and then basically the insurance company just had to pay. We had to come up with a number the insurance company could, and the company could live, and the government could live with, because it turns out the engine manufacturer had to be bonded, which meant that if anything like this happened, the insurance company was going to have to pay the difference. So they didn't care what the number was, but their insurance company cared, and the government cared, because they were going to get the money back. In any case, erosion, that's an example of where they're using a very expensive braze alloy because of the erosion problem. And we run into the erosion problem fairly often, so far as that goes. Now, let me just introduce, anybody have any questions? Let me just introduce this, and tomorrow we'll talk about contact strengthening, and then we'll actually get into fusion welding, which is what most people think this course is all about, but we're just past the halfway point right now. on lectures. We mentioned contact strengthening back with adhesive joints. The thinner the joint, the stronger the joint, at least in tension, and we'll go through this in a little more detail tomorrow. But this comes out of the Brazing handbook, and this is the joint thickness in inches, but it's on a log scale, so this is 10 thousandths of an inch. This is, oops, I'm sorry. Yeah, this is 10 thousandths of an inch, 1/1000th of an inch thick, 1/10 of a thousandth thick, and here it's getting to be millionths of an inch thick, 10 millionths of an inch thick down here. I'm sorry. Thickness, diameter, well, I'll have to look at it. Anyway, that's pretty close. As you get thinner and thinner, the joint strength goes up to over 110 KSI. And actually, it wasn't adhesive bonding, it was diffusion bonding when I talked about the merging steel and they put the silver activated layer in between. They got very, very strong joints over 100 KSI, whereas the silver, this is actually, in this case, it's cast silver. This is actually a different problem, but where they actually brazed it. But this is the ultimate tensile strength of the silver. So I've got a joint that is steel, silver as a braze, and steel. Well, the steel is plenty strong, but why doesn't the silver, which has a strength way down here at 15 KSI, how can I have a joint that has 110 KSI when I pull it in tension? And you can clearly see a dependence on the joint thicker. The thicker the joint, the weaker the joint, until you get thin enough, and basically here, you don't get a complete joint. You have lots of voids, so the thing falls apart when you try to go too thin. But if you can get a good joint at 1/10 of a thousandth thick, you can get extremely high strength. And if you're at 3 or 4 thousandths of an inch thick, then you actually still get 50,000. That's a much better strength than you would expect. So tomorrow we'll talk about why that's so. Okay?